For lecture 5 of heat transfer, we're going to continue our discussion of a transient analysis with a spatial dependence. So this is effectively part 2 of that discussion. We had been talking about a plane wall analysis where we considered the wall to be symmetric, so we have convection on each side of the wall, or if we had insulation, then we can call the symmetry boundary condition at x equal to 0 the same as an insulated boundary condition at x equal to 0. And so we derived a solution for this problem, or derived the actual mathematical model for this problem, and then we're given a solution for this particular problem. We have a differential equation. This is our ordinary differential equation. Sorry, our partial differential equation involving x and time that applies at every point in the domain between 0 and L. We have boundary conditions, 0 slope at x equal to 0, a surface energy balance that conduction balances convection at x equal to L, and then we also have an initial condition that at time t equal to 0, the temperature is initially uniform at Ti. So Ti will be different, either larger or smaller than T ambient, and over time the temperature will evolve towards a uniform temperature. So I have this drawn in the case at which Ti is larger than T ambient, and over time the temperature profile looks uniform initially at Ti, but then over time decays down until it eventually is everywhere again uniform at T ambient as time goes to infinity. At that point, the wall is in thermal equilibrium with its surroundings. And so we are considering the case at which there is a spatial dependence, so T is varying throughout the thickness of the wall. It's a function of x and also a function at time. So I've drawn the profile here at different times, showing the evolution as time approaches infinity, how the temperature evolves from Ti to finally being T ambient. Notice that the slope I have drawn here, the slope is always 0 on this side. The temperature drops faster on this side than it does in the middle, evolving towards eventually T ambient. So that's our mathematical model, and then we scaled this by defining our excess temperature, put it in terms of theta. Theta is T minus T ambient. That made our ordinary differential equation or problem homogeneous. It made our boundary condition now homogeneous. And then we proceeded to scale this with a length scale L, a time scale L squared over alpha, and a theta scale being the initial temperature Ti minus T ambient. So we put this is all dimensional. We then put that in terms of dimensionless parameters. The parameters that we define then, we call, if they're dimensionless, we call them stars. So these are parameters you need to know. Theta star is equal to, it's defined as T minus T ambient divided by Ti minus T ambient. Alright, so at time t equal to 0, T is equal to Ti. That makes this 1. Alright, so theta star at T star equal to 0 is equal to 1. As time goes to infinity, so theta star as T star approaches infinity, this approaches 0 because T, as time goes to infinity, approaches T ambient, so this will turn into 0. So we have some bounds now in terms of dimensionless parameters. T star is defined as T divided by our time scale is L squared over alpha. Alright, this has dimensions of time. And then X star will be defined as X over L. So these are all dimensionless quantities. Make a substitution into the previous governing differential equation. I'm not going to go through the details of this again, but we end up with this new problem. our governing differential equation turns into this. Alright, so no alpha shows up in this. Our boundary conditions are theta star, derivative of that with respect to x star at x star equal to 0 is equal to 0. On the other boundary, partial of theta star with respect to x star, so this time we're at x star equal to 1, so on the right side of the boundary. This is equal to minus the BO number times theta star, and then our initial condition, theta star at time t star equals to 0 is equal to 1. So this is our scaled problem, well-posed mathematical problem that we can give to a mathematician and ask them to go to derive a solution for us in terms of only the BO number, and then it's our job as engineers to interpret those solutions and convert back to dimensional problems that we can then solve. Okay, so let's talk about what the solution looks like in terms of these dimensionless parameters. Hang on just a minute. So here's the profile in terms of theta star. Our initial condition is that theta star is uniformly 1 as a function of x star. So that's 1. That's theta star at time t equal to 0. Over time, the temperature will drop faster over here on this surface than it will in the middle. In fact, at very, very small times, the temperature profile is only going to be influenced over here near the surface, and it will remain uniform for some internal region for some amount of time later on. So the temperature profile will look flat and then have a very sharp curve at the outer edge. At a later time, though, eventually even the inner temperature will evolve and change as well. So we would expect the solution to look more like this, kind of a more uniformly distributed curvature throughout the entire body. The slope is always still going to be 0 over here, and as time goes to infinity, theta star approaches 0, which just means that our temperature is approaching T ambient. So our mathematical model is not concerned with the temperature profile through the fluid outside. So everything to the right is not included in our theta star solution. Theta star that we're given only applies to x values or x star values between 0 and 1. So the solution that's given to us is called a separation of variables solution. It's an analytical approximation, and I'll create a separate video that will go through and derive this particular solution, just so you know where it comes from for those who are interested. You're not expecting you to know that on the exam. We're just applying this solution for our heat transfer examples. So theta star, which is a function of x star and t star, then the textbook calls that t star the Fourier number. That is interchangeable in my notes, is equal to an infinite summation of a constant times a cosine function times an exponential decay. For each of these terms that are summed together, there is a C value and an eigenvalue, zeta 1. These are constants. And so this is an approximation by representing the solution as an infinite series. So this is a convergent series. So if you order these CNs 1, 2, 3, 4 as you get larger, as n values go up, the C value goes down. So C1 is greater than C2, is greater than C3, is greater than C4, is greater than ... That goes out to infinity for this to be a convergent series. Zeta 1s are also ordered. The eigenvalues are ordered a little differently. Zeta 1 is actually less than zeta 2, less than zeta 3, less than, and so forth. So these are called the eigenvalues for this particular problem. So this solution only works for particular eigenvalues. And so we're given value or ways to compute each of these C and zeta values that we would then put into that summation. So what this means up above is that if I were to write out every term, instead of showing it as a summation there, the answer is C1 cosine zeta 1 times x star e to the minus zeta 1 squared times t star. That's the first term. Plus the next term is, I'll write it down here, C2 cosine zeta 2 x star e to the minus zeta 2 squared t star. Plus another term, C3 cosine zeta 3 x star e to the minus zeta 3 squared t star plus dot dot dot. So that continues out to infinity. But since these c values are getting smaller and smaller and smaller, at some point it's fruitless to continue to evaluate what those c's are. So the spatial representation variation is represented with a cosine function. So you can imagine what the cosine function looks like, right? It's a zero slope at 0, and the cosine function drops down as you go out this way. So if you change this eigenvalue, you can effectively stretch the x-axis. So you're stretching out the shape of that cosine function until you get it to match this curve very nicely for the solution. For very, very small times, though, when there's a sharp curvature like this, you can't use just one cosine function to represent that. You need to use several cosine functions. It's still possible to do it. Several different cosine functions, all stretched at a different eigenvalue. If you sum those together just right, then you can come up with a very nice approximation to this, but it takes several terms to do that. For later times, for times t star or Fourier number greater than 0.2, it turns out that only one term is necessary. So we only need to include this one. C2 is less than 10% of C1. It's probably even less than that, actually, and it gets even smaller and smaller as the time increases. And this C3 will be even smaller than that C2. So from a practical perspective, there's no need to even include these for large t star values. So that's called the one-term approximation. So for the Fourier number greater than 0.2, right, which is the same thing as saying t star is greater than 0.2, then we're going to say theta star as a function of x star and t star is just equal to C1 cosine zeta 1 x star times e to the minus zeta 1 squared t star. So that's the solution that we'll use. These values depend on the beta number. Depend on the beta number value. And so those are tabulated for you. So you could actually use the formulas that are given and calculate those by solving the root. To solve for zeta, you need to solve that transcendental equation that's given for you. But I think it's easier to just use the tabulated version. Okay, so we've already worked an example that applies this solution and uses a one-term approximation. So whenever you do a one-term approximation, you do need to verify your Fourier number or your t star is greater than 0.2 as you work through your solutions. So that's just a kind of a review up to this point. Now what I want to do is I want to consider another situation or a different boundary condition. Instead of imposing out here a convection boundary condition that would arrive at a solution that looks like this. Instead, let's now impose, I'm looking for the paper, an isothermal boundary condition. I have some notes somewhere for an isothermal boundary condition. I'm still looking for them. I'm going to hit the pause button. Okay, I found them. So when we say an isothermal boundary, what we mean is that we will have an initial condition of Ti or theta star equal to 1 uniformly, and then we will presume that somehow instantaneously we're able to change the temperature of the surface at time t equals 0. We will instantaneously change it all the way to T ambient. So if if T is equal to T ambient, then T star is equal to 0. And so now if we look at subsequent times, first of all, there'll be an even sharper gradient for small times, but then at later times the temperature will still change and evolve till eventually even the midpoint temperature, midplane temperature, decreases over time. But notice that in this drawing, every profile passes through this point at 0 on the other side. That's the isothermal boundary condition. So this is different than the convective boundary condition. Here's the convective boundary condition, and where the surface temperature decreases over time, right? In this situation, an isothermal boundary condition, we're assuming effectively a step function for the temperature on the surface at time t equal to 0. We instantaneously change the temperature to T ambient over here. Okay, so we can easily get to that solution without rederiving anything just by taking the limit. For the convection case, take the limit as the BO number goes to infinity. So the boundary condition at x star equal to 1 for the convection case is the partial with respect to x equals minus the BO number times theta star. That's what's applied right here at x equal to 1. Okay, so take the BO number to the other side. So solve this for theta star at 1. Alright, so 1 over the BO number now, or minus 1 over the BO number times d theta d star. Well, now let's take the limit of this as the BO number goes to infinity. Then you see that theta star is going to 0. So in the limit as BO number goes to infinity, theta star is equal to 0. Alright, so theta star at 1 is actually the temperature of the surface minus T ambient over Ti minus T ambient. That's the definition of theta star. Alright, so in the limit as BO number goes to infinity, that surface temperature then must be equal to T ambient. So in the case when BO number goes to 0, the surface temperature is instantaneously, so as a step function, imposed to be T ambient. So we have a nice convenient way to model a situation where we have an isothermal surface. Model an isothermal surface if we're going to say the surface is instantaneously enforced to be Ts at time t equal to 0, so like a step function. All we then need to do is let theta star be redefined as T minus Ts over Ti minus Ts. Alright, we're just replacing T ambient with Ts, and then go get theta star solutions that we already have for convection, but get C1 and zeta 1 values that correspond to a BO number equal to infinity. And that is provided for you on the charts. So that's a nice, interesting little way that we can get to an isothermal boundary condition using the solutions that we already have. So now I want to work an example for you with an isothermal boundary condition. I'm flipping pages here. We're going to work this example. So problem 5.3 and an older edition, Binker, Perel, and DeWitt. I'm not sure which problem that corresponds to in your current edition. So in a tempering process, a glass plate is initially at a uniform temperature. It's suddenly reduced, or it is suddenly cooled by reducing the temperature of both sides to Ts. So it says suddenly reducing the temperature of both sides. For us, that effectively means instantaneously. See if I can fit the word instantaneously in right there. So that's what gives it away, that they're not giving you a heat transfer coefficient. They're actually telling you we are instantaneously imposing an isothermal condition on the surfaces. I think it's on both sides. So the plate is 20 centimeters thick, and the glass has a thermal diffusivity of 6 times 10 to the minus 7 meters squared per second. It's initially at this temperature. It is cooled by reducing the temperature of both surfaces. So we're reducing the temperature of both sides. Right, okay, so let's draw this. Here's our glass thickness. So we're going to assume symmetry. Right, we're going to have, instead of convection on both sides, well, we'll start with an initial condition. Let's first draw. We're going to start with a uniform Ti throughout the entire thickness. So let's call that 2L all the way across. And we're assuming that at time t equal to 0, we're going to impose a surface temperature, Ts. And so at a later time, small later time, the temperature at the surface will be Ts, but it still takes time for the internal temperature to lower. So temperature profiles will look something like this as time is increasing. Still notice that I have a 0 slope always at x equal to 0. So on the other side, it would look like a mirror image, right, where that would be the same Ts. I'm just not drawing that side. So Ts is imposed instantly. So it's not a convection problem. So there really isn't a BO number. There's no need to check. Say, oh, is the BO number small enough to use lumped capacitance? We're going to take the BO number to infinity. Right, so that's not, there's no BO number check for this problem, and then we're going to redefine theta star to be equal to T minus Ts divided by Ti minus Ts. Okay, so it's asking us to find the time that the mid-plane temperature, that it takes for the mid-plane temperature to reach 50% of the maximum possible temperature reduction. So the maximum possible temperature reduction would be for the entire thing to reach Ts. Right, so the maximum reduction is going from Ti to Ts. So we want to know how long does it take for this center line temperature to make it to halfway between these two. So part A is asking for find the time at theta star at x equal to 0. That's the midplane. When is that equal to 1/2? Part B says find if Ti minus Ts is equal to 300 degrees C. Find the maximum temperature gradient in the glass at the above time. So part D, they're actually going to give us some values for Ti minus Ts equal to 300 degrees C. Find the maximum partial of T with respect to X. The maximum temperature gradient, the gradient is the partial of T with respect to X. It's referring to a space, so a spatial derivative. It wants to find us the maximum value, so let's put maximum there, over this entire domain at the time that was arrived at the previous answer. So at theta star equal to 1/2. Okay, so let's look at finding the time at which theta star at x equals 0 equals 1/2. The solution for theta star for a plane wall, we'll go get that solution. Is actually, I'm just going to write it out, summation of n equal 1 to infinity Cn cosine zeta n x star e to the minus zeta n squared t star. Right, but we are going to assume that it takes enough time that we get past a Fourier number or t star equal to 0.2. Let's assume that first, use a one-term approximation, and then verify it later. So we'll assume the Fourier number is greater than 0.2, and we can't forget to verify later. So if it's greater than 0.2, I only need the first term out of this series. So theta star then is equal to C1 cosine zeta 1 x star e to the minus zeta 1 squared t star. Alright, that t star is the Fourier number. Okay, so we want to find the time at which this, at x equal to 0, is equal to 1/2. Right, so let's go ahead and write theta star. Actually, that's called theta naught. Theta naught is actually defined as theta star evaluated at x star equal to 0. That's the midplane temperature. So if I plug in x equal to 0, x star equal to 0 above, cosine of 0 is 1. So this is just equal to C1 e to the minus zeta 1 squared times the Fourier number. I'm still going to call it t star. Okay, so what we're going to do now is call that 1/2 and then solve for t. Actually, let's go ahead and let's call it t star. T star, if you do the algebra, take this c to the other side. So I'll end up with, and then take the natural log, and then I have to divide by minus zeta 1 squared. T is equal to minus 1 over zeta 1 squared times the natural log of 1 over 2 C1, just doing the algebra. Right, and remember that that is the Fourier number. So now we have to come up with values of C1 and zeta 1 that correspond to a BO number equal to infinity. So we're going to go to table 5.1. Let's see. I can find, here's a copy of table 5.1. Using table 5.1, following the BO number on the far left hand side, BO number gets larger and larger and larger and larger. As the BO number gets larger, these numbers change less and less and less. As the BO number limit, as the BO number goes to infinity, that looks like that's pi over 2 is probably what that one is. Alright, so these are the values that we want. This is zeta 1 in terms of a radian and a C1. So zeta 1 is 1.507. C1 is 1.2733. Zeta 1, 1.5708. C1, 1.2733. Be careful and don't read the wrong or mix up the columns there and call this one C1 or vice versa. So if we now calculate T star, which is actually the same thing as the Fourier number, substitute those values, we get 0.3788. Right. That is larger than 0.2. Right, so that implies one term approximation is valid. Take time to communicate that. So now to solve this for the time, T star, remember that T star, or the Fourier number, is defined as the time divided by L squared over alpha. Alright, so now solve this for the time. Take the time scale to the other side. It's L squared over alpha times that Fourier number, or T star. Alright, so 0.01 meters squared divided by alpha is given as 6 times 10 to the minus 7. Make sure you get that minus included. Meters squared to the second. So notice the meters squared are going to cancel. The seconds in the denominator of the denominator move to the top. I left off the Fourier number that must also be included there. 0.3788. The final answer for the time is 63 seconds. So it only takes 63 seconds in this case, which kind of makes sense that it would be a fast time, at least faster than a convection boundary condition, because we're imposing that step function in the isothermal temperature of the surface. Okay, so part B now says, if we go back to the problem, part B gives us a temperature difference, Ti minus Ts at 300. It wants us to find the maximum slope that's in the glass. This, you can imagine, might have something to do with thermal expansion, and we're trying to prevent the glass from cracking, so they want to know what the temperature gradient is in the glass. And so if we go up and look at what we expect the temperature profile to look like, notice we have a zero slope on this side. It's maximum over here on the surface. So just from understanding what we would expect the temperature profile to look like, I'm not going to go through any derivations or proofs or anything. We're just going to say, hey, the maximum occurs over here on the surface at x star equal to 1. Alright, so we need to find, so for part B, we're going to find the partial of t with respect to x at x star equal to 1, or x equal to L. Alright, so this is dimensional, not starred. So in fact, because of that, let me change this to x at x equal to L. Alright, so if that's the center line and this is each side, the profile is going to look like this. Right, the maximum of value occurs here, maximum gradient at x equal to L. So we need to come up with a way to evaluate this. What we have is a solution for theta star, right? Theta star, remember, is defined as T minus, in this case, Ts over Ti minus Ts, right? And we also have x star as equal to x over L. Our solution was theta star was equal to C1 cosine zeta 1 x star e to the minus zeta 1 squared. Fourier number, I'm going to put T star there. Alright, so we can take a partial of theta star with respect to x star, but that won't be the same as the partial of t with respect to x. But we can convert it, right? Because we have the definitions. We know how to get between theta star and t and x star and x. Alright, so the partial of theta star, let's go ahead and take that first. Partial of theta star with respect to x star is going to be equal to the constants. Let's go ahead and move those over to one side. If I take a derivative of cosine, right, I get a minus sign, zeta 1 x star times the derivative of what's inside, so I need to multiply by zeta 1. Let's put that in square brackets. Right, okay, and so now what I want to do is evaluate this. We want to evaluate this at x star equal to 1, and at t star equal to, what do we have for t star up above? 0.3788. So I'm going to put t star value in. I'm going to substitute 1 here. So I'll have sine of zeta 1 times zeta 1. And there's a minus sign included in that as well. This ends up equaling at minus 0.7855. These are dimensionless quantities over here, the stars, and so this has no units associated with it. This is dimensionless. So the question is now, finally, how do I make the connection back to the temperature? The temperature, let's use this equation up here, solve for the temperature, is equal to Ti minus Ts times theta star plus Ts. So the partial of T with respect to X at X equal to L is going to be equal to, I'm going to scale this partial of theta. I'm going to take the T out, or let's make a substitution for partial of T with respect to X. Put this equation there, and that'll convert it to partial with respect partial of theta star. That constant will come out front. So this will be equal to Ti minus Ts partial of theta star. There's the numerator. The denominator, and so X is equal to L times X star. If I put this in place there, and L comes out front, and then I have the partial with respect to X star. So that's my connection. I simply need to multiply that above. So the partial of T with respect to X, in this case, at X equal to L, is going to be equal to Ti minus Ts over L times the number we have above, minus 0.7855. Okay, so you have to be careful of units of these 300K. L is, what was it, 0.01 meters. The number ends up being very small, so I'm going to convert the units to millimeters. This is minus 23.57 degrees C per millimeter. That's the maximum gradient in the glass. Okay, so the key for part B is how to figure out the connection between the partial of theta with respect to X star and relate that to the partial of T with respect to X to get that gradient. Part A, I think, was pretty straightforward. Just we had to find zeta 1 and C1 for BO number. That corresponded to BO number equal to infinity. Okay, so the discussion to continue now would be to take these concepts and apply them to a radial problem. And so for that case, the problems look very similar, with the exception that the solution that's given to you for theta star now looks a little bit different. And so as an introduction for that, actually we're at 38 minutes now. I think what I'll do is go ahead and create even another lecture. So we'll call this lecture 6. We'll focus on the radial component, or the radial problems. So I'm going to stop this lecture now. So that concludes lecture 5.